Hello. Oh, what has happened to my hair? Ooh. Terrible stuff. Neutrino got pipped. There we go. That's just how it goes. Morning, Mountain Ash. As always, hi again. If you're new to the stream, do say hi in chat, or I don't want people to feel left out. I recently told some people that I told some people about my live streams. We'll see if they find us. Oh, Twitch says I'm unstable. Stream bitrate too high. And maybe off. And this thing says offline over here as well. I'm going to refresh that and see if that makes it just go away. Yeah, it still says unstable. We're just going to pretend that's fine. Streaming, eh? Much harder than you might think. I have a slightly different plan for today. We've been doing number theory forever. My plan today is that I need to get ready to teach a tiny bit of teaching for next term, and I thought I'd do that on the stream to show you what it's like revising material, planning ahead, and also because the content's kind of cool. So I'll put that all together. Hi, Mary. Good. I don't know why I'm laughing so much. I think it's because of the chaos of. I've got a lot of different things open. Let's see. So, what am I doing? I've got the course information on the page, on the screen. We're going to have a look at that. I'm going to try and explain what this is. We did a tiny bit of this on the stream at one point a few months ago. I don't know if people remember, but at some point on the stream, I tried to show off this sort of thing. Let me doodle a little bit. It's this thing to do with finding the shape that minimises the shape of a hanging chain. I just feel like we've done that problem. There's sort of some maths that you can do to help you minimise that. To find the shape that minimises the total gravitational potential energy of a chain or something that's hanging between 2 points. Yeah, there's some tangent there. It's a fun problem. We tried, so I've got this version of it where you try lots of functions. Yeah, you try lots of functions, and then semi-magically the answer turns out to be cosh, hyperbolic cosh. So something like this, up to scalings or whatever translations. And in the kind of warm-up problem that I wrote for my students, that I think I talked about on the stream, that kind of appears out of nowhere. This is the course where you learn why it's cosh, or where that bit of the maths comes from. Maybe I should load up that problem because it's fun. Let me just throw it on the screen. I'm kind of proud of it because I need more things on the screen, right? Is this the right file? Yeah, this is the right file. There we go. So this is an introduction question that I wrote. I think I've shown people this before, but you know, it doesn't have to show people things twice. First stream after Quest for the Quintet. Yeah, that was a long time ago though, right? Yeah, okay. So maybe a long time ago, I told you about this sort of mathematics. The answer is so the idea is you're trying to minimize maybe something like this, where you've got some integral that takes a function and returns a number. That's what integration does, right? You supply a function and it analyzes it, adds up the area underneath, maybe returns a number. Here, there's a sort of wider class of integrals that you might be interested in, where it takes the function and also maybe the derivative of the function and does stuff like that. So this is no longer the area underneath y. We're not integrating just y. We're doing something complicated involving squaring y and also squaring the derivative of y. So this is a complicated object, and understanding how this works, or how large or small this might be, is kind of the question. Why is there a vertical line there? Oh, I've made it go away. If I were an architect, all my buildings would have cosh ceilings and elliptical shaped rooms. Oh, like the St Paul's Cathedral thing, right? So that's what you're referring to. People can look it up. St Paul's Cathedral has got, I think, elliptical shaped gallery or something. Okay, so this thing's positive because it's got squares inside. It's an integral of positive stuff. So for any real function y, this thing is some positive number. Maybe 0, but probably not 0. To be 0, y would have to be 0 all the way along. And actually, I've forced you to make it 1 at these two endpoints. So this is like me imagining holding up the ends. This is not quite the integral for potential energy of a string, but it's kind of close, and it's got the same answer. So it's a good warm-up problem. Anyway, so the way this problem works, and I've just sent this off to my students to see if they'll have a go at it before the course. Hi students, if you're watching. Is to calculate what this is for y equals things like x squared, which means to put in x squared over here, and 2x, the derivative, over here, square each of them, add it together and integrate. That's some function of x, you could do that. And you put other functions in as well, including weird stuff like cosh, because my students know about hyperbolic functions, so I can give them those. The weird bit, the bit that's actually good in this question, is that if you write y as cosh x over cosh 1 plus f of x, then this satisfies both these conditions. This bit satisfies both conditions, so f would have to be 0 at both endpoints. And then you can do some lovely integration by parts. You can take this stuff and shove it up into the integral up here, and it just kind of simplifies nicely. You do some integration by parts, and it turns out, oh yeah, it's what you thought when we integrated this bit, I of cosh x over cosh 1. It's got all of that stuff in it, kind of from multiplying out the squares here, right? Things like y squared, y of x squared, I'll take this and I'll square it and I'll get a lot of stuff, but including cosh x over cosh 1 squared. I'm going to stop highlighting stuff, it's not going very well. Plus a load of other stuff, and the other stuff turns out to be positive. So that proves that I of y is always bigger than or equal to this. This is the function that minimises that integral. But the key idea of the course coming up is to work out what property it is that cosh has that means that when you do that integration by parts over here, I said I'd stop highlighting, I lied. When you do this integration by parts, there's a property that cosh has that makes it all work out. It satisfies a particular differential equation. Okay, it was a lightning fast look at what this course is about. But the sort of things we're going to see as we skim through some lecture notes and look at what's in the course, the things we're going to see are integrals that have, wow, it doesn't like me highlighting that integral. Ha! We're going to have integrals with functions and derivatives of that function inside, and we're going to try and turn that into a differential equation for the function that minimises that integral. Tricky things to remember along the way is this integral sort of shaped thing takes a whole function and returns just a number, and we're trying to minimize that number on the outside. Choose the function that does that. Okay, so I'm getting ready to teach this like next term. If my students are watching, they can get a head start. I wonder if they are. I don't think so. I think they've got enough maths already. But yeah. So this is not just motivated by physics. I mean, this lets you solve some physics problems like minimizing energy, but it's more fundamental. This gives you a way to reformulate physics in terms of minimizing integrals rather than solving differential equations. Now, those maybe sound like just two equally advanced topics from the A-level point of view, right? Because maybe you don't have to solve very many differential equations yet. But if I point out that things like F equals ma, Newton's second law, F equals ma, that's a differential equation. It's talking about the acceleration, which is the second derivative of position. So it's a differential equation. You can turn that into a question about minimizing an integral. Now, why would you want to do that? Well, you can turn lots of sorts of physics into minimizing this integral and get kind of a new unified idea. It's called the Lagrangian viewpoints. Viewpoints? Or what's the word that people say after Lagrangian there? Lagrangian physics. What do I want to say? So it doesn't just thank you. Well, Waffle first time chat, helping me out brilliantly, thank you. Lagrangian mechanics, which is the idea that you minimize. This is the sort of thing I want to get. This is the sort of thing I want to revise before I'm teaching this next term. The idea that you're minimizing something. So there's two ways of thinking about how light works, or at least two ways. One is to think that light satisfies the wave equation, which is a differential equation. And the other way is to think that light tries to minimize the time taken along a route between points. Do I mean time taken? Relativity. That's a can of worms. Minimize distance, maybe? To take a geodesic. Light tries to take the shortest route in some sense from A to B, which is like minimizing something. And you can use that to build, rules of optics. Yeah. Lagrangian mechanics. I have sneakily opened a Wikipedia page on my left. On my left screen over here. Because this is the sort of thing that it is in the course, I should know it, but linking it into modern physics, which I haven't studied modern theoretical physics in years, so I have to keep revising it and remembering. Something like the Standard Model is, I think, an example of let's just minimize this object. Because I think that's what action is. And I think the Standard Model is just some massive tensor expression for the action that we're minimizing. This is the sort of thing I would like to try and revise on this stream. Right, okay. Right, let's get rid of this. So this is a sort of warm-up question which I think you can do with like A-level methods, because once you know about integration by parts and cosh and integration squaring, once you know about squaring, you can do this question. And the value, if you do this question that's on the screen now, you can prove that tangent of 1 is less than 16 over 21, which is a ridiculous thing to prove, having just done some integration. 16 over 21. I don't write step questions. And this is probably not hard enough. Lots of this is not hard enough or interesting enough for a step question. But there's probably a step question in here somewhere. Anyway, right, good. Okay. Let's get rid of that. Let's not look at the lecture notes yet. Let's try and remember what's in the course. So I think revision for me means trying to remember which course is this? How does it link with the other ones? What do they know when they get here? What are they trying to learn in this thing? So I've got some learning outcomes. This is the course overview written by the lecturer and iterated year on year, so it's only slightly changed year on year. Okay, overview, finding the minima or extrema, so maybe, okay, fine. Usually minima for me. Quantity over a system that has functional degrees of freedom, okay. Like you can change the function. I think that's what they're saying. Anyway, pure and applied maths and physics. Problem in geometry of finding the shape of a soap bubble. I'm going to find the shape of a soap bubble. Surface that minimizes the surface area. Good, okay. People heard about these sort of shapes of soap films minimizing surface area? So because of surface tension, soap films want to minimize, or want to is too strong, but soap films are stable when they minimize their stable is an entirely different kettle of fish. Stable soap films stop moving when they're minimizing surface area, which you can write in terms of some horrible integral. Right, okay. Principle of least action is now the standard way, there you go, to formulate the laws of mechanics and basic physics. Hello, Kobold. What is that? This is page-back calculus variations. We're learning it. It's the standard way to formulate the laws of mechanics and basic physics. And this is an introductory course in the second year. The A stands for second year of the Oxford Maths degree. I'm doing some tutorials on it next term, so I'm trying to remember what's in it. It's a short course, so I'm only actually meeting my students twice. 2 problem sheets. Excuse me. Right. Give rise to a system of differential equations. Brilliant. Called the Euler-Lagrange equations. Direct methods for analysing solutions. Good. Methods for far-reaching applications to help develop students' technique. Help develop students' technique. I can never mind. Students were able to formulate, this is very brief, and analyse them Fine, okay, good. Okay. Is this integral or what? I don't know what you mean. We're going to have loads of integrals. Surprise. Jump scare. Here are some integrals. Ugh, this is the first problem sheet that I've got to do with my students in month and a half. There's only 2 problem sheets. So we're going to find extremals. So first we've got to learn what an extremal is, I guess. Key learning outcome. Maybe you mean integral like the course platform. This is not that. Okay, so they need to learn about variational problems and Euler's equation, and they're going to learn about axisymmetric soap films. Okay, good to know. Now we'll have a check for the lecture notes to see what they... wonder what they actually do. Oh, okay, right, axisymmetric. Yeah, okay. And I should probably look up the double bubble problem, because I like to mention bubbles when I can, and double bubbles especially. So I should, and it's fun to say double bubble, so I think I should get ready to talk about that in a tutorial if I've got time. The famous double. Several dependent variables. How does principal? I can't remember which one that is. I'm really bad at names of things, especially when the names are people's names. I'm just so bad at these. Is it just how Hamiltonian dynamics works? Oh, I can't remember. Okay, good revision for me. I also can't remember what holonomic means, but that's okay. Geodesics on surfaces, fine. Extension self-independence. Yeah, okay, I remember how to do this. And then Lagrange multipliers right at the end. And eigenvalue problems for Sturm-Liouville equations. What about Legendre polynomials? I explain these course synopses. You have to then go and look at the lecture notes, because the course synopsis will just say Legendre polynomials, full stop. And I'm thinking, my students are going to learn something about Legendre polynomials in this course. Let's find out what. Okay. So I also like to have to get a sense of the level we're working at to remind myself what sort of tasks they're being given. I do like to have a quick look at the problem sheets. Also helps remind me whether or not I can do the problems without thinking. I know the Euler-Lagrange equations, so I'm going to be okay here. These ones have got boundary conditions, which I suppose I'm going to go and apply, because we're going to find... Yeah, it's just a matter of solving the thing. And then this one is weird because it's got plus y of 1 squared. And there's a hint. Adapt it. Yeah, okay. And I vaguely remember there's something weird that happens because this y of 1 is at the boundary of the integral. So it's like a different... Anyway, never mind, okay. There's a weird thing of adding on y of 1 squared. Okay, make some more Lagrange equations. So standard kind of problem sheet question where it's like, show that is this natural boundary condition. Oh yeah, okay, so you get some natural boundary conditions. There's secretly some integration by parts happening, and you want a term to vanish, so it's probably that. Okay, and they're going to learn to do it with y prime prime in there as well, so I have to remember that my students are going to learn some content, and then the question sheet is going to ask them about some slightly harder content with an extra term in here. And talk about, first integrals. Okay, so that question's actually fine. Yep, good. Maybe they learn... I'll check the lecture notes, but maybe they actually learn this in the lectures, and then the question's about doing something with it. Okay. And then find extremals of these things with y's and z's in there, which I remember doing before, and it's a bit messy, but not too bad. Okay. And then on sheet 2, they're also going to learn... oh, you want the link of where we are? We are here. It's not a book, but it's just some online lecture notes for an Oxford course. Oxford courses, almost all of them have just got lecture notes on the Oxford Maths website. For maths, sorry, just for the maths course. Maths is great. What other courses do you need? Okay, so I've got to remember my students are also going to learn this. And yes, second derivative stuff, but it's fine. They're just, by this point, really good at this sort of thing. Extreme limit function y, 0 boundary conditions, and a constraint. Right, they need to learn the Lagrange multiplier stuff. And what is going on here? Loads of UX, UI, UZ stuff. Okay, I don't remember how to do this. So this is learning for me. F from R7 to R. Oh, because it's got 7 inputs. That's fun. Oh, right, okay, so this is like the wave equation stuff, right? No, maybe not. Maybe not. Oh, you can use this to build something that relates. Right, hang on, okay, getting there. Right, this lets you formulate Laplace's equation in an integral form, I think. Yeah, because this one turns into some nice differential equation on the left, Laplace. Ooh, okay. No worries, pack all blood. I can link you to any Oxford Maths course you like, or if you click on the links on that page, you can find all of the other ones they've got. Yeah, good. And then some Lagrange stuff at the end, which I've just been teaching a course called Differential Equations 2, which has got loads of this stuff in Sturm Liouville form. Okay, so personally, I'm not too scared about these last couple of questions now that I've thought about them. Good reminder that these things are coming up. Okay, right, time for some lecture notes. Bam, right, okay. And I've got double bubble, and I want to learn about Lagrangian mechanics, because I think it's a bit of a blind spot for me. I know that this is relevant to modern physics. I say that sometimes, and yeah. Imagine says, do you not teach the same courses each year? I actually do. But a year's a long time, and in between, I have to be careful not to forget stuff. If I don't do the prep work, then I found that my tutorials are kind of like a photocopy of what I said the previous year. Not like a handout that's photocopied, like the experience of me saying stuff is like a photocopy of the previous year, and you can get away with that a bit, but if you're not careful, you end up doing like a photocopy of a photocopy of a photocopy of a photocopy, and it's lost all definition. Because I'm not a researcher, and I don't actually use any of this content on a day-to-day basis, I also have to be careful that I don't forget what it is or how to do it. And also, I like to try and do better every year. I like to try and up my game a bit. I've got half an idea to make a couple of little resources or make a couple of little extra things to give to my students to help them understand. I'm not just going to run it back from last year. Okay, I don't know. Maybe in a different world. Maybe if I were a researcher, or maybe if I were better at remembering things, then maybe I would be able to just run it back from last year. But I've tried doing that, and it doesn't go well. So prep. You're also keeping me honest by doing my prep on stream. Look, it's forcing me to actually think. It's very easy to glance at the problem sheet and be like, yep, that's the same problem sheet as last year. I remember doing that question. You just saw me say that, but now I'm actually going to force myself to do the hard bit. Right, because it's a short course, there's space for me to try stuff out or do something a bit weird or different with the tutorials. I use it as a tiny bit of a test bed, a little bit of an idea, which is why I've got this like warm-up question, right? The warm-up question was seeing like, if I give a warm-up question before the course, can my students get an idea of what's in the course before we start? Okay. So let's see. I'm not going to go through this in the same way that I was going through number theory for the last couple of weeks, where we went through number theory trying to like learn number theory and really interrogate all the statements. I'm trying to remind myself what's in there and identify things that I've personally forgotten or maybe never understood. And you don't want to get caught out by all the students turning up. All the students turn up and they all know the same examples, really, because they've all been to the same lectures. You don't want to not know that example. You've got to know the same stuff. Okay. Yeah. So reformulation. Here's a phrase that I want to use. This is a central point of the course. This is nice. To show how abstract and non-obvious ideas can play a part in solving concrete problems. Brilliant. I think you can put a sentence like this at the start of any good course. reformulation of Newton's laws, F equals ma, into Hamilton's principle. I had a go at saying this out loud a minute ago. Much farther in part B, so this is third year, classical mechanics. I don't know if any of my students are planning to do part B, classical mechanics, but it'd be nice for them to have the option to do so. So nice for them to get ahead. These short courses that we're doing in the summer term are supposed to be helping students get ready for third year courses, or pick up a little bit more unrelated maths. So there's some on techniques that will be useful in third year, and there's some on just sort of graph theory, number theory, stuff without any prerequisite knowledge. That's goes there. Q chat, why can't we do the number theory one instead? But hey, I'm teaching calculus of variations. Okay. Right, basic principle. Maxima are stationary points. You should differentiate it. Yes, there you go. Okay, good. These notes basically extensively on those of James Maynard and Andrew Hodges. Huh, nice. Shortest path. The length of the path is given by this. And here's our first example of I of y. And yeah, so this reminds me that the course uses square brackets because it's a functional that assigns a real number to each number function y. I should maybe try to use square brackets for consistency. Maybe my warm-up problem should use square brackets. I'm not sure it matters that much, but I'm not really one for details of the notation. Q, somebody at some point will explain to me why it's super important to use square brackets, but it's a map from continuous functions to the reals. That's a function, right? I don't see why we need a new name for that. Okay. It is a function, right? It just definitely is. I'm not being weird. I guess it's defined on other things as no, okay, I'm happy. This square is positive, so the integral is minimized if that derivative is 0. This is sort of boring. Okay, we've deduced a local rule about what happens at 1.5 global criterion. That's kind of cool. Generalize considerably and apply to a wide range of problems. Yep, good. Okay, nice intro. Here's the biathlon problem. Oh, I love this. I think I've used this on Maths Club at least once. There's a picture on the next page. What's this up here? They need to cross a field, then cross a river. How do you get from A to B? Look at the picture. Nope. Where's it gone? There it is. So got to get to. This picture's not perfect, is it? I think B is supposed to be over here. Yeah, I think we've done something like this. The idea is that I sort of draw my own picture. Wait, ignore this one. You're going to get from A to B, but you're really slow moving over here. No, wait, maybe you're fast over here. This is like the beach, and this is the sea. So you're slow at swimming. So you shouldn't just run from A directly to B. So run and then swim. Get in the water and swim to get to B quickly. Because your running is faster, you should aim more like up here and then go in that direction. I think we've done this on Maths Club at some point. The standard A-level way to solve this is to say there's one parameter that matters, which is this point, when do you get in the sea? Which is, if that's the y-axis that way, we could say that that's got coordinate y. I think they're calling it yp over here. Yeah. We're choosing yp to minimize the total time. And then there's some Pythagoras for the lengths of these lines. You allow for the speeds, and you want the derivative of that function to be 0. Dog calculus, right? Because the idea is that your dog can do this. Your dog knows how to minimize this function. If you throw a tennis ball or something in the sea, and your dog sees it and knows not to run in a straight line, but to run over there and swim, how does your dog's behaviour compare with the minimum of this function? Can your dog do calculus? The answer is lovely. and suggests that something really good is going on. It turns out to be this thing, which is Snell's law. There's a relationship between the angles. If you interpret these things in terms of angles, there's a psi1 and psi2 angles in that picture. So maybe your dog just knows Snell's law? Physics, right? And it's the same thing that light does. So the idea is that light knows how to do this derivative as well. If you throw a tennis ball in the sea and you want to shine a laser at it, then you shouldn't shine a laser directly at it because it will get refracted when it changes medium and goes into the water. The light knows that the fastest thing it should do is to go that way and get in the medium over there, and then it's Snell's law says that the bend as it goes into the medium through which it moves slower will get it to the point B, which is why the tennis ball will appear to be over here somewhere in that direction. Actually look at it. I think I'm now imagining a kind of 3D sea. The idea underneath here is that photons and your dog behave in kind of the same way. They're both trying to minimize something. Maybe time that it takes to get to a point. That you can... And if you don't really believe that anything's trying to minimize anything, then hey, you can just do the maths, right? To find... It's still an interesting maths problem to minimize the time. Or if you like, minimize the weighted distance. A weighted distance, what do I mean there? So there's a distance here, but it's got some weighting on it. It's multiplied by a factor. This one 1 over c1, this one 1 over c2. Right, hang on, let's learn this bit then. Fermat observed that Snell's law follows from such a least time principle. Not until the 20th century that such a principle could be understood in terms of quantum physics. Now, I don't know any quantum physics, if I'm honest, so I don't know what that means. Is this like the idea that light kind of does everything? Is there a principle of least action in quantum mechanics? Let's put it on the list. So least action in quantum. And that's a reminder to me to go and look at like the quantum mechanics. If I really want to know, I need to go and look at the quantum mechanics reading list or notes or something. How do I go back? Oh, I can't go back. Okay. I have to scroll back through. There we go again. Okay, so I'm already thinking maybe I want to... Can I fix this image? I think half of it's missing, so maybe I want to put point B in as half the word swim. Least action formulations of quantum mechanics. Is that a thing that you think the claim from Waffleoff in chat is that Feynman did some of this? Okay. Muddy field problem. Okay, I've seen the muddy field problem before, so I'm excited by this. Running on a muddy field that occupies the region x equals 0, x equals c of x. So their speed, instead of having a big strip of beach and a strip of sea, it's more of a continuous transition where this bit is slower, but then it's faster over here. No, maybe the other way around. Sorry again. Faster, slower, but like a gradient or something. Yeah, continuously varying refractive index. Ugh. Which is something you might think of if you've seen, I don't know, you've seen a stack of, what would this be like? A stack of different media? No. Okay, maybe not. Maybe not a thing you've seen. It's a good practice, right? I can say nonsense in here. Divide up the muddy field into strips of thickness dx. Repeatedly apply Snell's law. So it's true that this thing... Yeah, I don't really feel like we're doing various principles yet so much as very carefully applying Snell's law, right? Yeah, look at the angle. This gives you some differential equation. So the way to... And this is slightly specific to the particular problem that we're looking at, but the big picture here is that we started with an integral to minimize. Is it even an integral? It's not quite an integral yet. We started with a sum of things that we wanted to minimize. bit for running on the sand, bit for running in the water, or now it's a sum across lots of tiny bits, kind of an integral. I'm going to turn it into a differential equation. What is that? That's the same again. Okay. And then we're combining those into a differential equation. Fine. Yeah, okay, so this is the fun one where c of x is x. Speed is faster over to the right. So we're imagining something like this, where there's a kind of slow lane and there's a fast lane. And the further right you go, the faster you are. You want to get from like A to B, maybe? This is a problem. I'm not quite sure if it's the one they're describing, but if you imagine you're on the motorway, I've drawn it the British way around. Americans, please invert your screen. So I've got the slow lane on the left. You want to get from A to B, and the rule is the further right you drive, flip that in America, the further right you drive, the faster you're allowed to go. That's the fast lane. But obviously you have to go over to the fast lane. You want to get to B. You're planning to like leave the motorway at some point. So maybe your route looks something like this. You go a bit into the fast lane and then you come back again when it's time to leave the motorway. And I've drawn that kind of skewed so that you gradually get into the fast lane and then suddenly remember it's leaving over there. Urban chat. You claim you like maths? Please name 10 maths. I think you're being asked for your favourite sort of maths. Or something you liked from Maths Club, maybe? I don't know why you've been picked, but hey. So this gives you circles. You go through and you solve. We haven't really started doing variational principles yet, right? Because we haven't got any integrals. Okay, turns out to be circles. Okay, so I should remember that they do this example early on, but not in terms of an integral. It's not that hard to phrase it in. Not that hard to phrase it in terms of an integral, right? What would you do? Says it's not that hard, proceeds to think about it quite a lot. So what would you do? You'd have, if you have some curve y of x, then moving along that curve takes you time. It takes you time where for each bit dx, that takes you a lot of time for two reasons. One, because you actually have to move a distance 1 plus y prime squared dx along, because this route is at an angle. There's a little triangle going on here, dx here, dy dx, dx on the right, and a right angle, and oh my goodness, Pythagoras, distance here. So that's one reason. And the other reason is that your speed might be really slow. So I should take this distance and divide it by speed. And then that's going to take you a long time to get all the way from A to B. So we're looking at integrals like this, root 1 plus y prime squared over c of x. And later on, I think this is going to be an interesting group of these. 5, 6, 2, 1, right, okay. Right, okay. Chat is off on a different adventure entirely. Different speeds, different places. Okay. What are we doing? What are we doing? Oh, there it is. Well, did I just write that on the side while it was right there in front of me? Something I do, isn't it? Yeah, okay, great. Right, I should stop preempting what's going on and just read. Integral that we're trying to find the extremals for, probably minimum values. Far more general problem. That's what we're going to do in this course. We've got a function that depends on x, y, and y prime. Okay, good. Pick up the pace a little bit. I think this is fun, but need to speed up. Yep, good. We're still going to use square brackets. A single method that deals with all such questions. This is why I like teaching this course. There is a single method. There's only one thing in this course, really. There's only one trick, which means it's not too hard to explain to students. You show them the one, you make sure they know the one method. Okay, independent of coordinates, that's nice. Not shortest distance or shortest time, but least action. Okay, that's going to be later. So I should revise that. Good. Ooh, string and superstring theories. Okay. Okay. Vary function nearby, metrical topology, okay. Okay. Right, okay. Bump functions. Cavalier approach, nice. Okay. You don't have to answer that. I'm not certain if I'm a pro mathematician. I think it depends if people are paying you. Nobody's paying me to do this. And here we are. So I think I want an actual picture of this, because this looks fun. This looks fun. Yeah, there's all exponential decay and polynomial growth. Is there a picture of this in the lecture notes? Can I have a picture of this? There's no picture. Where's the picture? No, wait. My next page is broken. There's still no picture. And then the test function lemma. There should definitely be a picture of this. Why is this considered a sketch proof? There's some maths hiding in here. This thing would actually be slightly, not necessarily hard, but just fiddly. It's the sort of thing you do a few times in first year analysis courses. I'm not a big fan of doing it. Please don't make me do it now. But there's stuff you can do to make that work. Yeah, these properties are obviously true. So that's the one that's sketchy. Not in a bad way, just technically we should probably go and prove that. Right, I'm going to Desmos this because I kind of want to get a better idea of what we're doing here. I think I know. So it's like, I think it's supposed to be from the name. Where have I gone? There I am. I think it's supposed to be this, but let's try and draw it. Okay, what am I doing? X, and then there's a minus, and then it's x to the -1. Already fun. 1 minus x to the -1. That bit. What? I mean, okay, can I multiply it by like 10 or something? Yeah, okay, I feel much better about this now somehow. Right, I get, okay. So the plan is that this function is non-zero in some region, and you can squash it down and stretch it to make some interesting function that's non-zero in some region. But it's also really nice. It's infinitely differentiable over here. The exponential is just good. It means that it's so flat. This is why it's sketchy, because I say things like, "Oh, the exponential is very flat." It's a snake that ate an elephant. It's a snake that ate 2 elephants. I prefer, I want it to be a little bit taller, I think. So what am I going to do to think about why that works? In case a student comes to me and says, "Oh, that was quite a sketchy proof in lectures. It's non-examinable, but how do you actually prove that?" I think I want to imagine or just check that I understand why this thing has 0 derivative at the origin. Is that obvious? I mean, I can differentiate it if I have to. Nobody's making me differentiate it. Maybe I should. Yeah. What am I doing here? So let's note say exponential dominates the polynomial growth, and I'm feeling daft. Why? There's my polynomial. I mean, 1 over x is 1 over a polynomial. Is that what they mean? Let's just prove it, right? So when x is very small, this is very large and very negative, so you get 0. Right, then the derivative is going to have some, right, the derivative is going to have some stuff like this, isn't it? Minus x to the minus 2, x of minus x to the minus 1. That's where the polynomial stuff is going to come in. So this thing also goes to 0, because mumble, this thing goes to 0 faster than this thing goes to infinity when x is small. I prefer to think about large values, so I would make the substitution u is 1 over x and think about this function, the behaviour of this green function as x goes to infinity, rather than thinking about small x. And now this is very much a kind of polynomial exponential thing, where mumble exponentials beat polynomials, and this sort of product, even if you put a 3 or a 4 up here, goes to 0 if you make x large enough. There it goes. Blomph. Couldn't have picked a better example. How high does that go? Does that go really? Oh my goodness. Okay, great. I'm no longer illustrating anything, it's just a great big green L. Phew! Had myself worried for a bit there. Times 34 by mistake. Thing was clearly going up to infinity. I really believe that it comes back down again. Comes back down again. Over here. Goes to 0. And it's a sketch proof because it says, instead of proving that properly. How do you prove that? L'Hopital's rule, right? So you prove this with like L'Hopital, where you have this thing. You want to know, maybe it would make more sense to do L'Hopital on the previous thing, but whatever. You want to know if this thing goes to 0 or not. I guess really maybe you should do it the other way up, so it's both sides, both top and bottom going to 0. Yeah, never mind. Anyway, as you differentiate, L'Hopital's rule says that you should differentiate, and as you do that, you're going to decrease the degree on here, but you're going to get exponential again on the bottom. So you get this kind of, you can do a little bit of induction there. Okay, so that's what's going on with this, and that's why all the derivatives, because the derivatives are going to keep spitting out just polynomials, but have that exponential protection in there. And that's what's going on with this. There's my little hat again. I really do want to put a factor of 20 on the front there. My little bump function. It's infinitely differentiable, so no one can at you and say it's only defined between 0 and 1 and it's 0 out. Sorry, it's only non-zero outside between 0 and 1. Sounds a bit suspiciously discontinuous, but no, it's continuous. It's 0 on both endpoints. All matches up nicely, and it's nicely behaved as it comes in. And then the derivative is also nice, so no one can at you. Okay. Right. I feel like I want to try and get that picture into Lynch notes. By scaling, assume it takes the value 1 at the midpoint. Oh, right. Okay. Well, if we can fix that. Okay. Right. So I've always wondered this. There's some interaction with a part A course I don't teach called integral transforms. So possibly I should go and learn integral transforms a little bit as well. let's put it on the list here. Bump functions are in integral transforms, which is of course of no interest to you watching the stream, because what's an integral transforms course? But it's interesting for me as I get ready to talk to students who are taking this course, because they might have also done integral transform. Okay, right, I haven't skipped back to where I was. That was where I was. What have I done with these nodes? I think I've imported it twice or something. I've got the weirdest thing going on here where my thing thinks this is a 60-page document. It's actually a 30-page document with every page in here twice. So what have I done? What have I done? Can I fix this? Probably not. We could look at it in here. Okay, yeah, let's just do it like this. Okay. All Lagrange equations, I know this bit. So there's some integration by parts, which helps you convert this. You say if you're at a minimum, then whenever you add one of these little bump functions, that should increase the value of I of this integral. Whenever you add a little bit of a bump. Let's point at bits of this. This is a bit too technical, I think, to go through in detail. But hey, do I love this? How much do I love this? Whatever. Oh gosh, okay, maybe I should learn what a regular distribution is. So yeah, like how, so you imagine what's happening if you put in y plus a little bit of a bump function or a little bit of any other function to say, I'm looking for the minimum shape or whatever that minimizes this integral. So if I make any little variation, then I should get 0. And as you change alpha, the kind of small parameter there for how much you're going to change it, that's a standard A-level kind of differentiation problem where you have one parameter alpha that you're changing, and it's supposed to hit a minimum when alpha is 0, because the actual function y is supposed to be the minimizer. So this is like you imagine in the 1D stuff you do at A-level, it's like looking a little bit to the left and a little bit to the right of the value. If it's a minimum, then that should be a bit bigger. And you can, like differentiation, you can find points that satisfy that. It corresponds to this idea that the derivative is 0. Good, okay. So minimizers give stationary values, good. Yeah, that's what I just tried to say out loud. Constrained minimizers give stationary values, okay, fine. Yeah, you look at bump functions that have 0 on the edge, okay. Right, here comes the Euler Lagrange equation. So it's how to turn this sort of integral, where you're integrating some function of x and y and y prime. Don't get too distracted by f. That's like a name for the action of squaring y prime squared, adding them together, or it's the name for the action of squaring adding 1, square rooting divided by c of x, that sort of stuff. Don't worry too much about that. The key idea is still that we're taking a function y and we're doing some stuff to it. Right, the minimizers satisfy this and natural boundary conditions. Proof. And they do this quite a lot of times. It's kind of the only idea in the course. On screen now, the only idea. Okay. So derivatives. So this is some differentiation. There's some partial derivatives in here with the weird curly shaped d, because this is big F is a function that depends on lots of variables. Lowercase y is fine, it only depends on one variable, but big F depends on lots of variables, so they've got these partial differentiation going on. And they're imagining the only thing that's going on here is to work out how, if you plug in y plus a little bit, differentiate with respect to alpha, it has a kind of predictable effect on the right-hand side. There's some chain rule stuff going on here to say, well, okay, when you change alpha, then y changes a little bit. Also, y prime changes a little bit. It changes by alpha e to prime because you differentiated it as well. Okay, good. Then use integration by parts to eliminate this. Get rid of that. Integration by parts, and yeah, there's a subtlety of the argument here that I need the students to really understand. Not so much people watching the stream, but my students need to understand that there's a little subtlety here to talk about eta vanishing on the boundaries versus eta not vanishing on the boundaries. I want to think about those bump functions separately, and that comes from lemma 2.3, so it's kind of buried a bit. I have to scroll back up to look at lemma 2.3. Will they think about this too? Yeah, it's this C1 equals C2 equals 0. It's kind of dealt with separately. Choosing separate, you do these separate functions, eta that do 1, 0. Yep, okay, good. Okay. Check for understanding. Good, okay. Natural boundary conditions. Okay, so I think I can expect them to use the phrase natural boundary conditions for these things that come out. But importantly for us, there's a differential equation in here, which tells us if we've got some integral we want to minimise, then we can convert that into a differential equation. So much fun. Okay, and then there's a slightly different one if you've got fixed endpoints, where, oh gosh, right, okay, you don't get these natural boundary conditions at the end, but we're only going to consider functions that have 0 perturbations, only consider little perturbations eta that have 0 at the endpoints, so that all of our their functions will satisfy the boundary conditions. That makes sense to me. Okay, good. Right, okay, then they get shown some examples, but now it's just 2 examples. They're going to do shortest distance, straight line, fine, and the muddy field, they're now going to do it with this, brilliant, okay, and get out, yeah, okay, and get out circles. They're going to solve this. Separate question, can you solve this differential equation? A lot of multiplication and squaring, and then eventually some integration. Oh, what are people trying to learn? Fermat's theorem? Which one? Yeah, I'm with neutrino. Which one? Which one do you want to know? I could do Fermat's-Little theorem quite quickly. Fermat's-Little theorem is good. And Fermat's last theorem, I've got to delegate you to Andrew Wiles, who I work with. I had to do, a week ago, I did Fermat's-Little theorem with some visiting kids at local schools. It's great fun. Yeah. The hard bit is to having done the problem, to get people to sort of care about Fermat's-Little theorem and say, yeah, right, we've proved something that's actually good and useful and cool, and this is about as good as it gets. Right. Okay. Ignorable coordinates. Oh, because it simplifies. Enormous importance. Okay. Yeah, and oh, is this how? $1 million question. Is this how the Noether theorem stuff works? I think it might be. Let's control F Noether. No results found. Fun. Control F. So good. There's this brilliant result called Noether's theorem, where if you have, this is like a symmetry, or this is something that your integrand doesn't depend on. It doesn't depend on y directly. That relates to a conserved quantity. So conservation laws, like conservation of energy, match up perfectly with symmetries of the integrand, the thing we're minimizing, the, what do I want to call that, symmetries of the Lagrangian? Maybe it's not a Lagrangian. Something I need to revise. Noether's theorem is so good. And I think it's kind of, I think these are examples of what we've got here. Can't believe Emmy Noether's not mentioned in these notes. I've put Noether's theorem on my list of things to make sure I know. Every continuous symmetry of the action of a physical system with conservative forces has a corresponding conservation law. Rescue me, Wikipedia. Integral over time of a Lagrange. Okay, so I can say Lagrangian. Smooth, continuous and smooth symmetries of physical space. But there's this lovely table in here somewhere. Where's the table? Blah, 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 proof, blah, blah, blah. How does it work? Why is it true? Euler-Lagrange equations, the thing we've just seen. Ignorable coordinates. Yeah, okay. Oh no, the absence of the ignorable coordinate. I'm right. This is the thing in Emmy Noether's. Gives you a conserved quantity, a symmetry under some transformations. They're called. The distracting thing here is that they're called coordinates, like how x, y, z are coordinates. It's not quite that sort of coordinate. Right. Exhibit a symmetry. That's the idea. Perturbation theory. Here we go. Yeah, great. Okay. An infinitesimal transformation. Does it say that on this page? I think we're imagining continuous symmetries. So things like rotations and translations. Right, here are some examples. They're so cool. If your Lagrangian doesn't depend on time, so the Lagrangian corresponding to like F equals ma is just, you write down kinetic energy plus gravitational potential energy, I think. Anyway, so if your time invariance corresponds to conservation of energy, translational invariance corresponds to conservation of momentum, rotational invariance corresponds to conservation of angular momentum, and then are there more? I thought there were more. Okay, good stuff. So I think this course should say, "Oh, look, what is going on there?" Yeah, I'll go with that. I like that. But yeah, I think it's a good way to imagine it. Ooh, conservation of electric charge. Wow, what is going on? I scrolled too far. I dug too deep. I'm going to scroll further. I'm going to keep going. You can't stop me. What is all this? Wikipedia, you were supposed to save me. You were supposed to make things understandable. Okay, right, good. Try and get an impression of it. Field equations, up-down tensors, sort of maths I didn't do, Lie algebra, sort of maths I didn't do at uni. Right. Yep, cool, right, okay. Meme of small child running away from fire. Okay. Ooh. Wivlov wants to talk about general relativity. And I think the best thing for me to do, the thing where I save face the most, is to just not comment on general relativity. I think that the best thing for me to do on a chill math stream is to not pretend that I know any general relativity. Yeah, let's not pretend. Okay. What is time? What is time? What do you mean you're thing invariant over time. There's no such thing. It's not a helpful comment. Okay, back in Beltrami's identity. Let's see which one is that. F be a thing. What? Oh, if you can ignore one of the coordinates. What? Oh, hang on. Right. Okay. If in the context of this course where we've got f, x, y, y prime, x1 is x, x2 is y, x3 is y prime in this specific application, they're trying to say if the derivative, if f doesn't depend on x, then this x derivative, it's going to be 0. Integrate up, you'll get a constant. So you get a constant of motion or conserved quantity. Okay. So then we get to I love comments like this. Maybe this is maybe it's a good thing to say because maybe people want to know more. You want the link to Noether's theorem? Let me grab it for you. Noether's theorem. It's proved by Emmy Noether. Very quick, Emmy Noether. Emmy Noether is a German mathematician who made many important contributions to abstract algebra. Proved Noether's first and second theorems, which is the blue link for me. Symmetry of an action. Okay. Good, right, we'll read that at some point. What's the link to Hilbert? Invited to University of Gottingham. Okay. She spent 4 years lecturing under Hilbert's name. 1900s. Okay. This wants me to look at the Brooke-Histrocombe problem on MathWorld. So we can have a go at that. Click. I think I'll allow it. But this is just a MathWorld page about the Brooke-Histrocombe problem, which also doesn't have any images. Why are there no images? Or like a YouTube link or something to be like, I'm gonna watch this. Go on the hill. Oh, maybe I should 3D print this. I'm not gonna 3D print this. Right, good. My friend's got a 3D printer. I could. The answer. So this problem is find the curve that allows a smoothly falling particle rolling down, not rolling, but sliding down a hill to reach a given lying point, not immediately below the upper point in the shortest time. I think I've seen people build these. So this is a thing you can watch on YouTube of you build, to demonstrate, you build like a straight hill and you slide something down it. And you do it as a race versus a kind of graph that goes down and maybe up again. So if it's steeper, then the thing will move faster. Yeah, you can do best with some sort of cycloid shape. Let's look at the maths. The y is down in this to avoid minus signs. Okay, energy minus mgy is 0. Okay, this is feels a bit cheaty, but hey, okay, good. Total travel time is like this for reasons to do with kinetic energy, conservation of energy. We want the curve that minimises this, subject to going through 0, 0 and AH. And that is a kind of muddy path, muddy field. Speed proportional to root y, though, is different. Previously, we were thinking about it depending on x. Now we're thinking about it depending on y. Yeah, okay, fine, why not both? Beltrami identity, write it down, get a cycloid. We should really draw some cycloids. Let's quickly Desmos some cycloids. Have people seen these before? Love a cycloid. So I'm going to use T because Desmos loves T for this sort of thing. You can give it too many brackets, but hey, you can give it things like this, and it knows to put a range of values on T. I'm going to go from 0 to 2 pi, I think. maybe 8 pi, something like that. So you get this kind of picture like this. So I'm not fully convinced that this is the fastest route to get from anywhere to anywhere else. So what am I missing? What's phi? Ooh, no. No, those were x and y. Y is negative. There's a minus sign on that because of the height. And I guess, where are we trying to get to? Where are we trying to get to? Same, yeah. Oh, see this page for site mode for pictures. Yeah, I just, oh, there it goes. Oh, lovely. Oh. Oh. But that's also the quickest route to get from A to B. C chosen to fit based on A over H. Okay, I want to play with this a tiny bit. Let's find out. So, they said that you should put the number C in here. We're going to add a slider for C. So that's just going to change the size of this. And I want to make sure that it goes through the point A minus H, where I'm choosing where to put that point. So the only thing I need to do is to make sure that this brachistochrome thing, the red line, goes to the green point, which involves choosing the right value of C. That doesn't seem that bad. I reckon I can solve that. Let's go. That doesn't seem that bad. Wait, what's going on here? Because the ratio, in the ratio, the C is going to cancel out. So it's not that. Yeah, why can't I just choose the value of C? I want this thing to be equal to A, and this thing to be equal to H. Maybe that is hard to solve. Maybe not. So you use the second equation to solve for... How would you solve those equations to make sure the red line goes to the green point? I want it so that I can drag the green point around and the red curve follows to always go through. But if I put it over here, then... Oh, you just make C larger. Make it come back up again. Notes. Yeah, depending on the ratio. If A over H is bigger than pi over 2, I think it's interesting because it comes back up again. I've found a puzzle. Let's have a quick think here. So can I actually solve A over C is t minus, what function was I looking at a second ago? What function was I looking at a second ago? A over C is t minus sine t, and H over C is 1 minus cos t. Can I actually solve those? I'm not sure I can. So this one gives me like cos inverse of 1 minus H over C. So it's not very chill maths, but hey. Is equal to t if I rearrange this one. So then it's something like A over C is that cos minus, and then sine t is like square root 1 minus H over C squared. Probably, more or less, plus or minus. Can I solve that for C? Obviously not. No. These equations are horrible. Can I trick Desmos into solving it? So next question, can I get it to do numerics inside Desmos? Oh, I don't have my sound on. Thanks for redeeming channel points. Hydrate applies to everyone. That includes you. Don't get to stay hydrated. Okay, this feels like a good rabbit hole to go down. Hey, thank you. Wait, we're getting all the fluids now. Suddenly a fluid dynamic stream. Okay, give me 30 seconds to top up. I think I'm on coffee today. But I think, yeah, oh, Mountain Ash. And that's 4 times as many channel points. Tea time for everyone. I'm going to leave this on the screen and not running a break. We're going to think about solving this after a quick break. Back in a second with a coffee. That's the face of someone who doesn't know if he's live or not. Wait, chat's still going. Oh. Translating. Yeah, sounds about right. I am live. Whoa, anything could happen. Okay, plan. I'm going to stop looking at the lecture notes a bit. I think where did we get to? Maybe almost about sort of halfway through. So that feels like good preparation for, let's say, the first tutorial, where they learn the equations, apply them. I think I want to mess around with this Desmos thing. This is going to be a little bit silly. Something I've done before and I really enjoyed doing was getting Desmos to solve equations like this. There's a really stupid method that I know that gets Desmos to do stuff like this. So if I can build that, then I can live my dream of having the thing go through the point, and so that you move the point around and it shows you the brachistochrone for that problem. Quick look at where we are. We've got an equation. It's horrible. Not even certain I've got all the terms right. Yeah, okay. We're trying to solve for C such that A over C is equal to t minus sine t, where all of this stuff works out. We're doing that in the region, let's think. I'm worried about that. The signs on that sine t, very worrying to me. Can I fix that? Are we between naught and pi? I think we're between naught and pi. Let's have a quick look back at Desmos. Does it bounce at pi? No, it might not be. We're between naught and 2 pi. So I don't know the sign on sine. So maybe I shouldn't be using this kind of square root trick. That's going to cause me problems down the line, I think. Yeah. How am I going to do this? So first I'm going to try and find out if this thing actually has like solutions that are correct. So let's try typing it out. I'm going to type the right hand side minus the left hand side and look for roots. This is just super silly, but get rid of that. That was nice, but we can do more fun things over here. So on the right there, I've got, how does Desmos do this? Arccos is what it says. 1 minus h over x minus, and then this is the square root of, and I regret this term quite a lot, 1 minus h over c, h over x, sorry. I'm calling it x so that Desmos can show me different values, minus a over x. That was a disaster. What value of c are we supposed to take here? Kind of 3.5, and this thing is definitely not 0 at 3.5. So what did I screw up? Is it the sign on here? Yes, it is. No, it isn't. Tell me why. Why am I doing this at all? Tell me why. Do. Numerical solutions. We're gonna get there. They're a bit unfriendly. This is daft already. It's not even giving me the right value of c in this kind of simple example with normal numbers for a and h. Sensible numbers, just bring it over here. So I'd like it if this moved around and the root was at least in the right place, because I'm going to try and do some root finding. I'm going to do some root finding, it's going to be great. But this is looking like it sometimes has roots and sometimes doesn't, which is not really what I wanted right now. Well, that's a bit better. Still not great because it goes, no, that's it's looking all right actually. It's about 4 for the value of c. Oh yeah, we can work with this. Then down here, it would be more like, down here it would be more like 6 for the value of c. And if I set c to 6, that's pretty close. And if I'm up here, then this says it would be more like 1.3 for the value of c. And if I set c to 1.3-ish, it goes through. Okay, so I need to find the root of this equation. I'm happy with this minus sign for now. Over there, I'm much less happy with the minus sign. I could probably use some cases, right? Over there, I've got an idea. But we'll do the ones that are just downhill first. There's some region where, yeah, okay, there's some region where you can and cannot access this. Okay. So, root finding. How do we want to do the root finding? I think I want to do root finding in. So my favourite way to do root finding is to write a function and look for fixed points of the function to try and get this in the format x equals something. There are different ways of doing that. But instead of solving this equals 0, I would like to solve something equals x. I think I'm going to go for x is equal to a over this. So a over everything. Hey, thanks for the follow. Oh, this is going to be daft. This is going to be really bad. Yeah, not this. Don't do this. Let's not do this. Because there's a really fun method of just repeatedly applying the function, which if your function is not too steep, then it's all right. who was to follow from there? Wilson 1. Welcome to the show. About 10 minutes ago, people told me to go and make a cup of tea, drink some water, stay hydrated. That applies to you too. Wilson 1, sorry, I'm calling you out in particular. Welcome to the stream. Sorry for calling you out. Stay hydrated. Good, right. I like to try and pass it back to the audience as well. Otherwise, I feel like a Tamagotchi. You know, like you press the little button to give him a cup of tea. But this Tamagotchi fights back. That got weird. Okay. So I've got this equation. Oh, it kind of knows that. Can you get it to... This is the thing, right? It knows the value. 1.4 something. That's what I want. I want to extract that. I want to extract that solution from this equation, Desmos. How can you get this equation? 1.4 something so that it goes through the point. Tamagotchi, like those little 1990s things. Tiny little electronic device, little creature on it, and you have to keep it alive by pressing the buttons. That's what I feel like when people redeem hydrate. Yeah. There we go. This is such a daft way to solve this problem. Okay. How about I do cos? How about I wrap it all in the cos? So add that to the right hand side. Add that to the right hand side. Wrap it in the cosine. This is very silly. 1 minus and flip the h. So do h over that for x. Manipulate the equation into a silly form. That looks good. That looks good. So now I move this around and it's got an intersection where crucially the red line's got low derivative. So now here's the trick. We need a starting point, but we'll think of that in a second. So you define that to be a function. We've got a function and we're looking for, because I manipulated it in a silly way, we're looking for a point where the red curve, this function here, quick colour setting up. We're looking for a point where this red curve meets this line y equals x, which you can do with a kind of cobweb diagram of repeatedly applying the function. So long as you've got a good starting point, what is my starting point going to be? I suppose it should be, it needs to exist, doesn't it? So can I just set it to h? Is that all right? That makes that 0. Cos a over h is probably a real thing. Probably non-zero. Probably not 1. Okay, let's write f of h. That's a number. And then, so the idea is you just apply f lots of times, and it converges to the value at the point of intersection. So the first time it does f of h, and it looks up on the red curve what f of h is, and then you apply it again, and it looks that up, and it's a bit closer because the red line's flatter. So you get a bit closer again. This is a bit sensitive on where you start, and it's a bit sensitive on how you rearrange your function so that you get something nicely behaved near the intersection point. But messing around with it, you sometimes get something that works nicely. That looks pretty converged. Sometimes when I'm doing this, if I'm worried it's going to take a few extra function applications to converge, you can do something like this, and then do this as g of g, which is to trick Desmos into doing lots of applications. It has not enjoyed that at all. Do I define my functions like that? Yep, there we go. Okay, so this will apply. This is like applying h 40 times or something. I don't really know how Desmos handles that, but whatever. And then all I need to do is to put all of this way up the top, so switch all the order of everything, and then just set C to be this. No slider. And now it should just go through the green point. Ha! Aha! Request the code! Yeah, so now it's choosing the right cycloid to go through the point. We did it. Provided I don't go over here, when it'll go really wrong. It'll not do it over there, but it will do it over here. So I think I just need some cases. Yeah, not happy. And the unhappiness is, yeah, just really bad, especially over here. Partly because the function, the intersection is no longer even not the right value anymore, because over here is where it should be a plus sign, and partly because the repeated function iteration is sending it off to somewhere weird. It's doing loads of weird stuff. Yeah, so we're going to set some boundaries. So what can we do? Let's get rid of these. Let's hide these. I think the problem happens, it's like the ratio of H and A. So I think, let's just stick in, I think it's this line. Oh no, it's like where the lecture notes had a thing about this. It's like this line pi over 2. Right, so below this line everything's fine. But the problem comes from if you try to go on the other side. Now it's bad. That's really bad. But if I put the green point over here, it's fine. So kind of bodge. I think, yeah, let's test this. I think if I put a minus sign in here, that it behaves well on the other side of the line. Bad. Very bad. Okay, I'm wrong. So kind of bodge would be to do the different sides of the line differently. Yeah, so this is a boundary. And it's to do with whether that sign term is positive or negative. The thing I called out of like, I put the square root in here, I've got a minus sign. I'm asserting that sine is the positive square root of this thing, which is not the case on the other side. And then my problem is that the function is badly behaved. So let's throw this back in again. I need to give it a different name. This function behaves differently over there. It just like looks like a different shape. Over there, I would like to have the minus sign, and then the function's just different. Let's try an x again. So I think I want to do different cases and only show the correct one. Oh, is that a thing you can do? We'll get there. We'll get there. Maybe we'll show 2 lines and you're supposed to ignore one of them. Oh, it's really glitching out. Let's hide this for a little moment. Like the correct version of C. See, this has got really steep points. I don't actually know which of these solutions I want. So I'm not very happy with this formulation. Okay, let's think. So what do I want to do? I think I want to copy this. I have a kind of C2 going on. Let's think. What values of C2 do I actually want? So this is going to be my new... What colour was this in? Purple maybe? This is my new one. And what do I want? I want C2 to be, in this case, something like 0.7. No, 0.8? 0.85? Oh, is this route over here? What is that? Thank you, Desmos. 8711. Okay, so I've got to believe in the process, right? If I can find that route in this other case, then we're good. What you do now? Yeah, what am I going to do now? Well, we're doing a cycloid. We're trying to find the right cycloid, this purple shape that goes through the green point. At the moment, what have we got? We've got hide that. At the moment, we have got some working stuff. So here's a cycloid, which is a curve of this form for a particular value of C. I'm trying to get the right amplitude or the right size of that cycloid. And as I move this point around, it's kind of working. Unless I try and get... There's this case where you want the cycloid to come down and then up again, which I'm not capturing well. It's not working over there. I kind of know why, so I'm going to do that case separately. Part of me just thinks I'm being daft and I should just multiply the thing. Am I missing a weird scaling that I could just do? Sine squared, cos squared sort of thing. Yeah, back into the equations. Back into the equations in a second. So this was one approach, but what about if I do this? So this is definitely true. And that gives me t. It's kind of the same, isn't it? Not quite the same. That gives me the point t. That gives me a relationship between the value of t at that point, where it's equal to a over h, equal to a comma h, and the value of c. The second equation comes from plugging that back in. So it is going to be nasty. This eliminated t. This way of doing it with the squares, sine squared plus cos squared, did not eliminate t. But maybe we can do something with this anyway. These ones cancel, don't they? So you get a squared over c squared minus, no, I don't love it. H squared over c squared minus 2h over c. I sort of wonder if I've got a different way in. This might go nowhere. That's already a bit weird. But this gives me a value for a t, right? In terms of c. It's not very nice. But then I can plug it into the other one and get some nice cosine sort of thing. I don't know. Yeah, it's plus or minus. Oh, is it plus or minus? Yeah, because it's the sign again, right? It's the same. It's the sign on sine. Problem. Okay, we go again. Plus and minus. Oh, who's Mountain Ash talking about? Oh, John Conway. Yeah. What did John Conway do with Philosopher's Football? I don't know what that's a reference to. Mountain Ash. Ecologist 7 says, how can you stand maths that's not useful? And they've picked the worst possible stream to do that in. They've picked, out of all the people streaming maths on Twitch, they've picked the stream. They've picked the stream that is about how all modern theoretical physics works. You couldn't have picked a more useful stream to say that on. Anybody else doing maths on Twitch, any other day of the week, you could have crashed a number theory stream or something, but no, you picked calculus of variations. Disaster. Right, so let's carry on finding the fastest route between these 2 points in physical space using calculus of variations and actually good maths technique. Oh my goodness. Oh, Philosopher's Football. I've got a website. Oh, we're opening we're opening a link on stream. Ooh, it's a game. It's a game. I've never heard of this. It works like this. Okay. Congratulations, you have sent me stream content. There are 19 rows and 15. 19 columns and 15 rows. X wants to move right. Oh, Noughts wants to move left. Here's the ball. This is a player. On your turn, you can place 1 in any unoccupied spot. Both players use the same pieces. Instead of placing a player, you can jump instead. It's the only way to move the ball. Jumps can be diagonal. The players are removed after being jumped. You can't pass. What, so you're jumping the ball over... Jumps can be chained and diagonal. Okay, so you've got some players and then the ball goes past. This looks fun. Left or right? Okay, I'm trying to get to the edges. These instructions are in a funny order. Cannot jump the same player twice in one move. Yeah, okay, fine. defender cannot continue a jump through their end zone. Okay. Oh, you can chain them. Oh, so this jump, you can jump like checkers over lots of chocolatey, but it doesn't have to be in a kind of straight line. Oh yeah, good point. Other people are not doing academic disciplines at all. Okay. Right, I'm probably not gonna. Randotron plays completely randomly. Okay, like should we play against a bot? Randotron. Play one as human. Right, okay. Let's see if we can learn how to play. Ooh, scroll bars. Yeah. Ugh. Okay, I'm gonna play some footballers. Where am I trying to go? Am I trying to go right? Is it their turn now? I'm winning. What? What? Oh, I don't understand what's happening here. Oh, I'm doing great. I won! I don't understand what I just did. Oh, it's like the I think I need to play against an actual robot. What, so you place this... Am I playing to the left? Or... No, what? What? I think I might have played against myself. Why am I only placing black? Oh! There's not two teams of players. The players are used by both people. So this is alternating to tell me, in tiny writing, to tell me whose turn it is. Right. So you might set this up, or you might want to do a jump. And the jumps look like this, where you can jump over strings of players. Right, I thought there were two teams of players. I'm such an idiot. Ah, right, okay. Yeah, that looks like a sensible move. Right, okay, I'm supposed to read this tiny text up here, which tells me whose turn it is. Okay, good-o. And the way you actually interact with jumps in here is not to click, but to... Good. Okay, right, we'll do this at some point, I think. But not right now. Accidentally play against self, not noticing, turns out alternating. Right, am I going to fix this in the next 15 minutes? Doesn't seem likely, does it? Seems unlikely. Those cases, that's terrible. Don't look at it. I'm so pleased with this iterative approach. I think you could play that. There was a two-player game. So Game of Life is an example of a game that you... Game of Life kind of needs 0 players, so that's fun. Okay, that's my boundary. Okay, we're back in. We're going to switch to looking at this one with a different value of C. Still want to understand how to make it go through that point. But we're going to rearrange this curve in a different way with a minus sign in here. And this does not look too friendly in terms of route finding. Has that just picked up a third route? It's got 4 routes. This is a disaster. It's never going to pick up the right route. That's going to be impossible to solve numerically. Find the correct route out of all of those. Wow, numerics is great. There it goes. Okay. Okay, so I need a drastically different function. And maybe I want a different function anyway. Let's go back to the equation. Oh no, it's disappeared, hasn't it? So let's type in the equation that we're trying to solve again. Which is, so don't forget this. Part of the kind of art of this method, I suppose, is to choose the right formulation of your problem out of all the ways to rearrange it. So what do I want? Not really this. Not really in purple, thanks. Let's go for a nice colour like bright orange. And let's hide everything else because it's confusing me. And let's put in, no, I want that back because that was my control parameter. Okay, so this was what we were doing before with the minus sign in. I also want to think about the one with the plus sign in, which, this function's not too bad, right? This function's really not too bad. Maybe I should be doing Newton-Raphson. I just can't be bothered to differentiate this function. Newton-Raphson is a kind of standard thing where you make you make a guess and then you follow the tangent to find the next one. So it's sort of maybe a better technique than just randomly guessing different forms of functions to throw at it. The urge to add random abs values, I missed that in chat. Just hope that it works. Yeah, I know. Okay. Is this the correct number then? So 6 and a bit. No, not at all. Where's the correct number? Thanks for the follow. I think you said you were French earlier. I'm not familiar with this thing of putting HHHH in chat. HHHH. Maybe that's a kind of French laughing noise. Genuinely new to me. Just trying to understand. So I'm still not right, which is a pleasant expression, pleasant feeling to have. Well, minus sign here as well. The temptation to throw random minus signs in. Why is it different? Because I've assumed this thing about cos as well, haven't I? When I wrote down this arc cos, because the arc cos came from a pretty naive take over here on the relationship here. Arc cos is always between, for I think Desmos's interpretation of arc cos, probably between 0 and pi. Let's have a quick look. Arc cos x in black is, oh no, I'm an idiot. Between 0 and pi, yep, good. Between 0 and pi. And this is precisely the bit where we would like value that is like 2 pi minus that instead. Right, so we actually want to solve this equation, I think. So this would say the correct value of C is like 0.9, not 6.7. 0.99. Oh yeah, okay, something like that. Okay, we might be onto something here. We've got a different equation. Right, the temptation is to just throw it all in the same bucket that we threw it in before, but now we've remembered about 2 pi minus. Oh, it's off the screen. So sorry. Off over chat. So sorry. This was some messing around with 9 and 9.9 and 9.5. So it's also, as well as being off the screen, it was on top of my bit of the screen where you're talking. So double problem. I can't see it and I can't see the warning message. Okay, so all I need to do in order to consider this stream done is to solve this orange equation numerically, solve the orange equation, plot it, and do some like cases so that both are on the screen, or one or the other, which is easier said than done. And it's not very easily said. Chill maths. It's like relaxing. It's not high stakes. It is my unprofessional stream. It means we're not taking it very seriously. Okay, let's try everything we tried before, but in a different order. We're going to go for solving this thing. We're going to pull this onto the left-hand side, ask for it to be equal to this with a minus sign, so it should still be 0.9 something, there it is. 0.9, oh yeah, what is that value there? 0.96-ish. Quick meme, solving equations, zooming into the x-axis to see the root. Yeah, perfect. Goes right through the point. That's what I want. I want it to go through that point so that when I'm moving this around, it doesn't do it yet, but when I'm moving this around, I want it to go through. So it shows me the brachistochrome. Which then tells me the implausible fact that if you want to get from A to B, don't build a ramp that goes very shallow. Build this exciting cycloid so that something sliding really picks up some speed on the way down, and then whoop goes up the other side, and it slows down on the way up. But overall, it takes less time than just very slowly drifting down a straight ramp. Good. Okay. What have we got? So this is tempting, right? Because cos of both sides. Maybe this is an error, but it looks like an error. Yeah, that was a terrible error. Look, I've introduced loads of extra roots. Don't want to do that. So there's why the step where I took cos of both sides introduces loads of roots. Don't enjoy that. I guess it probably did in the previous problem as well, but maybe it introduced them very far away. 10 minutes on the clock. It's becoming less chill every minute. Add the square root back in. Let's just try doing it the other way around, right? If it didn't work before, maybe it works now. Sort of pigeonhole principle for a divided by all of that should be x. Hey, that actually looks like it might work. That actually looks like it might work. Oh, look, everything goes to the same point. Solve! Find that point. That actually looks quite good. Different values. It's going to cross the blue line nicely. So yeah, maybe we just do this. Maybe this is F2. Not that. So this is the other idea for how to rearrange it that I had before, but now reused. And so G2 is going to be F2 of F2 of F2 of X. It's again my trick of getting it to apply lots of times, but without typing it lots of times. I'm so lazy. G2 of G2. I mean, I'm typing a lot of G2s now, so I have some amount of regret, I suppose. H? Yes, that's a number that's about 0.96. I think we might be there. We might be there, chat. That's looking good. Don't plot that, just tell me that and call it C2. Right, let's see if that's working for this value, I think. As I move the point, it changes. Let's see what we can get away with. I would like this down here and delete the slider. Hey, might be there. Might be there. Okay, so that one's working well for these cases and not working for these cases at all. That's kind of good. That means it goes away. Right, okay. There's something in this. Let's turn all of this off. Hide that, get rid of the X. Okay, so now we've got a case that works up here. And separately, if I turn this one back on, just to make it clearer what's going on, let's put it over here. We've got a case that works over here. Oh, and that one goes away. Brilliant. So all I need to do... Oh, it's not happy in here. Oh no, it kind of is. I'm just getting distracted by the one that's behaving really badly. All I need to do is make... Oh. The one up here is not actually that good. It's vanishing around here somewhere. Hide the C a bit. So this one was working well when I moved it around here, but it's not that happy if it gets close to the black line. I wonder why that is. Switch some of this back on. Why is it not happy over here? It's undefined. It should be... Oh, I guess okay, run into trouble with it not being defined to the right there. So if I was much better at thinking, I would start here and everything would be nice. Because it kind of always looks roughly the same. Like, how hard can it be to solve that? It's my initial guess is not very good. This is my initial guess. And when we're over here, the initial guess is just quite terrible. It's nowhere near the root. So I just want to make a better initial guess. And my better initial guess should be something like, where is that actually blowing up? I thought it was where h was x, because then this would be 1 and the square root would be 0. But it's not quite that. It's where this all together. Nice to see everybody's being safe on the internet. You don't know who anybody is, you don't know who I am. Ah, it's so annoying. Right, okay, this is an initial guess kind of thing. Can I make this better? Better intuition. Nobody's real. Nobody's real. When is this thing defined? Ooh, when is this thing non-zero? Ooh, terrible, horrible, nasty. I would have thought when h is less than x that this goes badly wrong. Oh, h over 2? What is that square root? 5 minutes on the clock. What is that square root? So when you square it, there is 2h over x and an h squared over x squared, which implies that there's some sort of problem. And a minus sign, which implies there's some sort of problem when x is h over 2. Yeah, okay, that's where I want to start. That's where I want to start, not at h, but at h over 2. So after all that, I think I'm just going to change this to an over 2. And it's still working. And still broken. Okay. Still working over here, still broken over here. It changes. So this is to do whether it's solving this properly or not. Whether or not this was a good thing. Nope. Whether or not this first guess was a good guess and it could successfully spiral in. Wait, can I just start way out to the right and it will find this and then... This thing's super flat, right? Yeah, I should just start at like 100 or something. Still broken. Still broken. What's f2 over 100? That's fine, right? That's basically the right answer. g2 over 100. Undefined. It's f2 of... Am I just doing too many function applications and it's getting confused? f2 of f2. Oh no, because it's coming down here and then missing. Ah, oh, that's annoying. So in the cobweb diagram, there's this kind of cobweb diagram where it looks at the value and then goes across the line and down and applies the function again, which near here is exactly what I want because it will take the value of the function, go across the line, and then apply the function there. And there's, actually, this is pretty bad because it's got derivative. It's pretty bad. It's got quite a steep derivative over there. Maybe I'm doomed to fail around there with this current method. You need quite a good guess for that derivative to work out. Can I cheekily fix that by doing some sort of squaring thing? Yeah, why didn't it break for the first one? The first one was really nice. It's a good question. My first one just looked like this. And the shape of this function is very different. It's got positive gradient, less than 1, which is nice. And if you put a large number in, then you get a large number back. So it kind of, the cobweb diagram just comes in from one side. I'm trying to imagine it cobwebbing in. You can kind of follow the grid lines, right? Follow the grid lines in. Whereas on this side, for the new function I've now given it, I'm not totally convinced this is the right approach because this is going to do, because of the negative gradient, the cobweb diagram does a kind of looping around thing and it seems a little bit unstable if the gradient's too large, which makes a bit of sense. The solution is probably something like don't write f2 like this, do a different version of f2. I thought I'd got lucky, but this is not a great choice of f2. There might be some brilliant way to rearrange this function that works for both and works well for both. This is the thing that I'd like to do. I'm going to save this for now and quickly show you. Oh, we didn't save that at all. Whoops. Cardioid quickly show you a different one I made that does work, that does something similar, just to convince you that this is a good idea. Oh my goodness, where did it go? Where did it go? I'm looking through all of my... I have way too many of these. Oh gosh, how many of these do I have? I have like 100, 150 saved Desmos plots. This one. This is the one that I'm really proud of, which is doing lots of horrible stuff. But this is the shape of a hanging chain. So it's a Koch curve, but selected so that it goes through both points and that it has a given length. And the idea is that when you move it, it's updating all the values of all the parameters in there. So you get this kind of realistic chain effect where it's got the right length, which works out so well in Desmos because this dashed line is length based. So you can kind of see that it's got the right length all the way around. It's got the right length and it's always in a Koch curve that kind of fits between. So this is sort of the realistic shape of a hanging chain with movable endpoints, which only sometimes breaks. It doesn't like having the 2 points at exactly the same height. But behind the scenes, this is doing the same sort of calculations. Quickly show you, physics engines are insane. Physics engines do not work like this in any way. Yes, you can change the length. Make the length smaller. You can put the points where you like. Yeah, I did make it so you can move the purple point left of the green point. Oh wow, this one works really well. Okay, I'm moving the point slowly because I'm scared. So this is doing the same sort of maths. I can't remember what that's for. Ah, yeah, this is a kind of circle to show you where you can reach. It breaks a bit when it gets stretched too tight. I mean, there are no solutions over here because it's too far away. So I put a kind of circle in case you wanted to think about. It just can't reach points over here, and it's not very good at the edges when the curve is very close to a straight line. It breaks there, kind of just before it leaves the circle. So I put this circling for that reason. But just to show you the maths. Oh my goodness, right, so there's all sorts of like hyperbolic stuff going on here with exponentials, but I found this way of rearranging. I think this is what I've got. Oh my goodness, no, this is some horrible combination, some horrible parameter given in terms of h and a. And then this is my function. It's got x in so many of these different places. And actually this is the function f that then combines those things together and looks like this, which is such a messy function. But it's carefully chosen so that the points where f of x is equal to x give you exactly the right value of, I can't remember which parameter in the question, but some parameter. Then I am doing hideous calculations over here, and I can't remember why. Good, maybe these don't matter. None of those being plotted. Why did I need n and h? I can't remember why I gave them such terrible names. And then h of... This is a separate calculation, I think. 0.2, I can't remember what that's for. Okay. I've lost the chain. There it is. So in the back end, it's doing lots of calculations. And just to be really clear again, this is not how physics engines work. But this is just me trying to find the solution. I would like this for the cardioid. I don't think it'd be as cool for the cardioid because it won't have that kind of physical. It won't have that kind of physical meaning of length being fixed, which visually feels right. But I would like to be able to find the cardioid between 2 points, and even if the equations are hideous. So here, the equation here is really nasty. You can sometimes do some numerical solution. I'm going to drop a link for this one. So, hanging chain. If you want to fiddle around with this, or try and work out what the hell I'm doing with applying. So here I've got the nested functions again. Good. If you can make this better, or if you've got ideas about how to make this work better or be less mad, then do let me know. Good. Okay. We didn't quite get there. We didn't quite get there with the cardioid. We got almost there. Let's plot the original one again. We got 50% of the way there. Hide everything. Let's do the wrap up for hide everything. We got almost there. If you want to go from here to here, here's a cardioid that minimises the descent down to that point. It can't cope with the ones where you need to go up again at the end. We're working on that. Good, right, okay. Thanks for watching. This is going on YouTube at some point. So if you're watching on YouTube, then my goodness, how did you find this channel? Maybe see you in a live stream at some point. I'll be back on next week for, I think probably, it's still the holidays, so I might still be messing around with this. I had half an idea that I'd start making some images, drawing some pictures to kind of check my understanding and augment bits where I feel like it needs a picture, so that I've got a kind of resource. Maybe I can bring it to the tutorial and say, look, here's a picture. I drew this, you can keep it. I didn't get around to that today, so we just have a circle. Yeah, and maybe we'll try and get this cardioid working. It's almost there. It's almost there. Ignore one of the lines. Ignore the line that isn't there. Right, good. Okay. Pi, yes. It's not that pi themed. We've got some problems. It's one of those ones where we do lots of different problems. I think there's some pi, but when we were planning it, we didn't. Yeah. We planned what the stream was before we selected the date. If you want to do a pi themed thing, you have to do the other way around. I'm sure lots of your favourite YouTubers will be doing pi themed content. I'm sure Matt Parker's doing another Pi Day thing. So you'll be out there getting some Pi content. See you Thursday for the professional stream. See you Sunday for the unprofessional stream. I will, yeah. See you around. Bye. That one. Yeah, take care. Oh, feels good not to have done number 3 for the 10th week in a row.